You're made of matter. So is your screen. So is everything you've ever seen or touched. But here's the problem. According to physics, there should be something else out there. Your mirror opposite. Antimatter. It's not a theory. We've created it. We've trapped it. We've even moved it between buildings like it was just another lab sample. And yet, despite all that, we still don't know why it's not all around us. Why isn't the universe just a glowing soup of radiation, where matter and antimatter annihilated each other? That's the question physicists at CERN have been chasing for decades. And in 2025, they got another surprise. Scientists working on one of CERN's most advanced detectors found something strange again. Something that shouldn't be happening, but is. It's not just that antimatter is rare, it's that it refuses to behave like it's supposed to. And the more we study it, the more it slips through our understanding. So, what's going on with antimatter at CERN? Why are scientists more puzzled than ever, even after building billion-dollar machines to study it? And is this mystery finally pointing towards something new? Something beyond the physics we thought we had figured out? The mystery starts right at the beginning of the universe. When the Big Bang happened, it should have created matter and antimatter in equal amounts. That's not a guess. That's what our best models say. For every proton, there should have been an antiproton. For every electron, a positron. And when those meet, they annihilate each other. Instantly. All energy. No leftovers. But look around. You're still here. So am I. And there's no visible antimatter drifting around. Galaxies, stars, planets, all made of regular matter. That imbalance is weird, because it shouldn't exist. Yet somehow, in those early microseconds after the Big Bang, something tipped the scales. Just enough for a tiny excess of matter to survive. And that tiny excess, that's what makes up everything we see today. We're talking about a difference of maybe one particle in a billion. That's how close it was, and the rest were all wiped out in mutual destruction. Now here's the thing, nobody knows why. Physicists call this the Baryon asymmetry problem, a fancy way of saying, where did the antimatter go and why did matter win? It's one of the biggest open questions in physics, and it's not just theoretical. If we understood what caused that imbalance, we'd be a step closer to understanding why anything exists at all. That's why CERN built experiments like the Large Hadron Collider, not just to smash particles for fun, but to study these tiny differences between matter and antimatter. Because maybe, just maybe, if we can catch antimatter slipping up, acting slightly differently than its mirror twin, we'll find the clue we've been missing. And this year, they finally saw something unusual. Again. Let's talk about something called CP violation, because that's where things start getting weird. In simple terms, CP symmetry is the idea that if you take a particle and flip it into its antimatter version and also reverse its spatial coordinates, like looking at it in a mirror and swapping it with its opposite, physics should behave exactly the same. That's the rule. At least it was supposed to be. But for decades, scientists have known that this rule isn't perfect. Back in the 1960s, physicists saw tiny violations of this symmetry in particles called kaons and later in B mesons. Those are both types of mesons, particles made of a quark and an antiquark. And even though the violations were small, they were enough to suggest that matter and antimatter don't always behave as perfect opposites. Still, here's the issue. Those mesons decay too fast, and their CP violations aren't strong enough to explain the imbalance we see in the universe. We need something bigger. Something that happens in baryons, the same class of particles that includes protons and neutrons, the building blocks of regular matter. And this year, it finally happened. CERN's LHCb experiment, which specializes in studying the differences between matter and antimatter, announced that it had observed CP violation in a particle called the lambda B baryon. That's a heavy particle made of 3 quarks, just like a proton, but with different types of quarks inside. And for the first time ever, physicists saw clear evidence that these baryons don't behave the same as their antimatter counterparts. That's a big deal. The asymmetry they observed wasn't huge, only about 2.5%. But in particle physics, that's enough to ring alarm bells. And the statistical significance, 5.2 sigma. If you don't follow the jargon, that basically means the chances of this being a fluke are less than 1 in several million. In other words, it's real. Now, this doesn't mean we've solved the antimatter mystery, not yet, but it gives us a new direction. A new class of particles where the differences between matter and antimatter might be stronger. And if those differences scale up, even just slightly over time, they could explain why matter survived the early universe while antimatter didn't. It's one of those moments in physics where the door doesn't swing wide open, but it does crack just enough for new light to come through. And suddenly people are paying attention again. Because if baryons like the lambda B behave differently from their antimatter twins, then maybe protons and antiprotons do too. Maybe the fundamental stuff we're made of isn't as symmetric as we thought. And maybe that's the key to the universe we live in now. But that's just one mystery. Because while the LHC is looking at high-energy collisions, something even stranger is happening in another part of CERN, where scientists are trying to do the unthinkable: put antimatter in a truck. You probably don't think of antimatter as something you can just load onto a truck and drive across town. But that's exactly what CERN is working toward. For the first time in history, scientists successfully moved a cloud of protons, stand-ins for antiprotons, across the CERN campus using a specialized mobile trap. They built a high-tech box to safely contain these charged particles and drove it about 4 kilometers across the facility, proving they could one day transport actual antimatter the same way. Why is that such a big deal? Because antimatter isn't just rare, it's absurdly difficult to handle. The moment antimatter touches regular matter, it annihilates. Gone. Massive energy release. So you can't put it in a glass jar, you can't freeze it or shove it into a metal tank. It has to be suspended, levitated, really, inside magnetic fields, inside a vacuum, inside a carefully engineered trap. It's like trying to carry a drop of pure sunlight in your hand without getting burned. So why take that risk? The reason is precision. While CERN's antiproton decelerator is great for generating and studying antimatter, the facility is surrounded by large magnetic fields from nearby accelerators and instruments. And those fields can subtly interfere with the delicate measurements scientists want to make. So, researchers developed a way to transport these charged particles to a quieter, more controlled lab environment, specifically to a facility in Germany with better shielding and less magnetic noise. That's what this mobile antimatter trap was for, and it worked. The device kept a cloud of protons, stand-ins for antiprotons, stable and isolated for over 12 hours through the entire journey. The fact that they could keep these particles secure during actual transport opens a door to new types of experiments that were previously impossible. Soon, scientists will be able to test how antimatter behaves in different environments, not just at CERN, but in other labs across Europe and eventually beyond. And that changes everything, because it's not just about studying antimatter where it's made anymore. It's about preparing to use it, send it, and push the boundaries of where we can take it. We've gone from generating antimatter in fixed detectors to proving we can transport protons, a critical step toward making antimatter portable. That may sound small, but in experimental physics, it's massive. It means new collaborations, new technologies, and far more precise tests of one of the weirdest substances in the universe. And all of this is happening while another group of scientists is asking an even stranger question. What if antimatter doesn't fall the way regular matter does? What if gravity treats antimatter differently? It sounds like a joke, like one of those shower thoughts people post online. If antimatter is the opposite of matter, does it fall up? Except at CERN, that's not a joke. It's an actual experiment. This is one of the strangest and most overlooked problems in physics. How does antimatter respond to gravity? If you drop a ball made of antimatter, does it fall to the ground like a regular ball, or does it do something else? Does it fall slightly slower, faster, or just maybe, does it fall the other way? That last one's unlikely, but nobody could say for sure until now. In 2023, two major experiments at CERN finally ran detailed tests to find out. One was called AlphaG, an extension of the earlier alpha experiments. The other was GBAR, short for gravitational behavior of antihydrogen at rest. These names sound technical, but what they were trying to do was incredibly basic. Make a small cloud of antihydrogen atoms, let them go, and see what happens. And for that to work, the atoms had to be neutral, no charge, because any electric field would mess up the results. The trick was to isolate pure antihydrogen and keep it suspended perfectly still inside a vacuum chamber using magnets. Then release it and watch what gravity does. Sounds simple, it's not. These atoms are insanely fragile. The conditions have to be perfect. And the fall distance, just a few centimeters. That's it. You're basically trying to detect the gravitational behavior of a ghost, but somehow they pulled it off. And here's what they found. Antihydrogen falls down, just like regular hydrogen. According to the AlphaG results from 2023, it accelerates under Earth's gravity in the same direction and at a rate consistent with matter, within experimental precision. GBAR is still working towards similar measurements, aiming to confirm these findings with even greater accuracy. Almost. Because the data also hinted at something strange. Just a hint that the acceleration might be slightly different. Not enough to break the laws of physics, but enough to make people squint at the numbers and wonder if there's more going on. A few results from GBAR were also a little off, though still within margin of error. Nothing conclusive, nothing headline-breaking, but not perfectly boring either. If antimatter does behave even slightly differently under gravity, it could crack open everything from quantum field theory to general relativity. Einstein's equivalence principle, the idea that gravity pulls the same on everything, regardless of what it's made of, has never been tested on antimatter until now. And while the early results suggest antimatter plays by the same rules, physicists aren't done testing. Because if they find even a 0.1% deviation, that would be enough to shake the foundations of physics. So they're running more tests, refining their measurements, increasing sensitivity. Because in this kind of science, it's not just the big discoveries that matter, it's the tiny differences that tell you something's broken. And when something's broken in physics, that's when things get interesting. But while all of this is happening, CERN's big colliders, gravity labs, and trap experiments, there's another antimatter mission gearing up to do something even bolder. They're not just dropping antimatter anymore, they're planning to send it to smash into unstable atoms on purpose. So where does all this antimatter actually come from? You don't just mine it, and you definitely don't find it lying around. At CERN, antimatter is made in one of the strangest and most advanced parts of the entire facility, something most people have never even heard of. It's called the antiproton decelerator, or AD for short. And it's exactly what it sounds like. A machine built to slow down particles that no one can touch. Here's how it works. First, high-energy protons are fired into a block of dense metal. The collision creates a shower of exotic particles, some of which are antiprotons. These are the antimatter version of protons, and they're born moving fast, too fast to study. So the AD steps in to slow them down. Not just a little either, we're talking about reducing their speed by a factor of 100,000 or more. Because you can't study antimatter when it's zooming around like a bullet. You need it calm, cold, almost still. That's where ELENA comes in. ELENA is a smaller circular accelerator that connects directly to the AD, but instead of speeding particles up, it takes them even slower. Think of it as a kind of cooling ring for antimatter. ELENA can slow antiprotons to just a few millionths of the speed of light, gentle enough to trap them using magnetic fields. And once they're slow enough, scientists can capture them in highly specialized experiments. There's alpha, which traps antihydrogen and tests gravity. There's base, which compares the magnetic properties of protons and antiprotons down to insane levels of precision. And then there's acicusa, which studies the internal structure of antihydrogen using laser spectroscopy. Each of these experiments is looking for the tiniest differences between matter and antimatter, differences that might explain why the universe is the way it is. If they find something, even something small, it could change the way we think about symmetry, time, or the Big Bang itself. But here's what makes this all so impressive. This isn't a giant collider smashing particles at nearly the speed of light. These are quiet, controlled, ultra-precise experiments. More like atomic surgery than demolition. And that contrast is what makes CERN so unusual. On one side, you've got detectors the size of buildings, where particles crash into each other at unimaginable speeds. On the other, you've got tiny chambers cooled to near absolute zero, designed to gently hold a few antimatter atoms like they're made of glass. This is the Antimatter Factory. Not just a single machine, but an entire ecosystem of experiments, each with its own niche, its own questions, and its own piece of the puzzle. And now, this whole system is about to do something even more ambitious. They're planning to take that carefully stored antimatter and fire it at some of the weirdest atoms in the universe, at unstable, radioactive nuclei. Because maybe the answers don't lie in smashing matter and antimatter together. Maybe they lie in how they interact. That's the goal of CERN's next big antimatter mission, PUMA. You've heard of particle accelerators, you've heard of antimatter traps, but now scientists at CERN are trying something that sounds almost too sci-fi to be real. They're going to take 1 billion antiprotons and bring them face to face with unstable atoms. Nuclei so rare and short-lived you can't find them anywhere in nature. And they're going to do it in a place where antimatter has never gone before. It's called PUMA. The name stands for Antiproton Unstable Matter Annihilation, and it's one of the most ambitious antimatter experiments ever planned. Here's the idea. CERN has 2 main research areas. One is where the antiproton decelerator and ELENA are, where antimatter is produced and slowed. The other is a place called Isolde, where physicists study exotic atomic nuclei, the kind that decay in fractions of a second, created artificially from nuclear reactions. Normally, these 2 areas never interact. Antimatter stays on one side. Radioactive nuclei stay on the other. PUMA is going to change that. Scientists are building a mobile antimatter trap, something strong enough to hold over 1 billion antiprotons, stable and isolated, for hours. The trap will then be physically moved from the antimatter lab to Isolde, where those antiprotons will be unleashed, not recklessly, but in a controlled beam, onto unstable atomic nuclei. Why? Because when an antiproton hits the nucleus of an atom, it annihilates with one of the protons or neutrons. And the debris from that annihilation tells scientists something incredibly precise about the structure of the nucleus it collided with. In other words, antimatter becomes a kind of microscope, a probe. It lets us peek inside radioactive atoms that are normally impossible to measure. This hasn't been done before, not like this. The hope is that by looking at how antiprotons interact with these exotic atoms, scientists can learn more about the forces inside atomic nuclei. especially in the so-called neutron skins, where unstable atoms tend to have weird, lopsided shapes. It could even hint at new nuclear physics, maybe beyond what the standard model can currently explain. And the really strange part? This experiment involves moving antimatter between buildings, by truck. That alone is a scientific feat. It's hard enough keeping antiprotons from touching anything in a static lab, let alone keeping them stable through transportation, temperature changes, and mechanical vibrations. But if PUMA works, it could change how antimatter research is done. It won't be locked to a single lab anymore. It could go where it's needed, brought to new experiments, new materials, and maybe even new countries. Antimatter might become mobile, and that opens the door to whole new types of research that haven't even been imagined yet. But despite all this momentum, CP violation in baryons, gravity experiments, precision spectroscopy, and now mobile antimatter, there's still a lingering problem. Nothing so far has fully explained the big mystery. Why is there more matter than antimatter in the universe? The data keeps improving. The tools keep evolving. But the answers, they still aren't lining up. You'd think with everything happening at CERN, the CP violation discoveries, the precision experiments, the antimatter drops, the billion-dollar detectors, by now we'd have found something big, something that clearly shows where the standard model breaks down, something that finally answers the antimatter question. But that's the frustrating part. All this work and the laws of physics still mostly hold. The experiments are impressive. The measurements are historic. But when you zoom out, they're all pointing to the same uncomfortable truth. Nothing we've seen yet is enough to explain why the universe favors matter. That CP violation in baryons. It's real, it's exciting, but the numbers still don't add up. The asymmetry is too small to account for the sheer scale of imbalance in the early universe. The gravity test with antihydrogen. So far, antimatter falls down like regular matter. No wild surprises, no weird repulsion. At least not yet. The BASE and Asakusa experiments, they're checking for the tiniest possible violations of CPT symmetry. The idea that flipping charge, parity, and time together should make no difference. But those tests have been so precise that any deviation would have already made headlines. And they haven't. It's like we're chasing a ghost. We know it's there, something must have tipped the universe toward matter. But every time we think we're closing in, the data just says, not quite. To be clear, this doesn't mean the experiments are failures. Far from it. Every result, even a nothing unusual, sharpens our understanding. It rules out wrong paths. It tells theorists where not to look. It closes doors so we can focus on the ones that are still ajar. But scientists are stumped, and they're not hiding that. In some ways, that honesty is what makes this more compelling. CERN isn't pretending to have all the answers. They're admitting that the universe is still hiding something. Something deep, something subtle. Maybe it's a new particle we haven't seen yet. Maybe it's a force we don't understand. Or maybe it's a breakdown of symmetry so small, it's like trying to hear a whisper in the middle of a thunderstorm. And that's the reality of modern physics. You can build the most powerful machines, run the cleanest experiments, trap the rarest particles, and still walk away with more questions than answers. It's not a failure. It's a clue. Because when the rules stop working at the edges, that's where discovery begins. So, for now, the antimatter mystery remains just that. A mystery. We've ruled out a lot of wrong answers. We've narrowed down the possibilities. But that final piece of the puzzle, still missing. And yet, it's that very uncertainty that keeps the scientists going. Because in physics, confusion isn't the end of the story. It's where things start to get interesting. The deeper we go into antimatter, the more the questions multiply. We've moved beyond theory. We've isolated antiprotons, trapped antihydrogen, watched it fall, and even packed protons, a stand-in for antimatter, into a high-tech trap and drove it down the road. And yet, the core mystery of why the universe is full of matter and not antimatter still stands, untouched. Why does matter exist? It's not for lack of effort. CERN's built some of the most advanced tools humanity has ever made just to get closer to that answer. And they're not done. LHCb is still running. The AD and ELENA are still feeding experiments. New missions like PUMA are just getting started. But none of this is about proving a theory anymore. It's about listening closely to what the universe is quietly trying to say. Because somewhere, hidden in all these results, is a hint of something bigger. Something we've missed. Right now, scientists aren't claiming victory. They're doing something harder. They're admitting the mystery isn't solved. And in a field built on answers, that kind of honesty means one thing: they're getting close. Because every time a result comes back almost, but not quite, it pushes us a little further out of what we thought we knew. And that's where discovery actually begins. So if antimatter keeps breaking the rules, good. That means the rules are ready to change.